Welcome you all. So in this session I will explain about how to solve the numericals on reaction steam turbines. Take down, see here this numerical example 1 or numerical number 1. A stage of turbine with the person's blading deliver dry saturated steam at 2.7 bar from the fixed blades at 90 meter per second. The mean blade height is 40 mm and the moving blade exit angle is 20 degree. The axial velocity of steam is 3 by 4th of the blade velocity at the mean radius. Steam is supplied to the stage at the rate of 9000 kg per hour. The effect of the blade tip thickness on the annulus area can be neglected. To calculate the wheel speed, second one the diagram efficiency, third one diagram power and enthalpy drop of the steam in this stage. So now list out the given data. Here dry saturated steam, so that is the dryness fraction is taken as x is equals to 1 and pressure is given as 2.7 bar and absolute velocity or steam is exited at the velocity of 90 meter per second, that is V1 is equals to 90 meter per second, and height of the blade is given, that is a 40 millimeter, so that is h is equals to 0.04 meter. The beta 2 angle is given as the moving blade exit angle is beta 2 is equals to 20 degree and that is equals to alpha 1, so according to the 50% of reaction turbine. Now Vf flow velocity is equals to, that's 3 by 4 times of U, then mass flow rate is given as 9000 kg per hour, so that is equals to 2.5 kg per second. That means that is 9000 divided by 3006 and then now we are getting that value is 2.5 kg per second. So now to find, first one is a wheel speed, that is N, second one is a diagram efficiency or blade efficiency, that is a delta B, then diagram power, that is power P, enthalpy drop of steam in this stage, that is a delta H. Now construct the velocity diagram, that is alpha 1 angle is given, that is 20 degree, then V1 value is known and draw the V1 line. So then draw the perpendicular line to the horizontal, that is Vf1. So here from the graph the Vf value is equals to 30.8 meter per second. So that is equals to, what about the U value? The U is calculated, that is 4 by 3 times of Vf, correct? So that is equals to 41 meter per second. So now mark the length of U, the blade velocity in a horizontal line. So now we know the value of, then find out the value of VR1 by joining the intersection point of the V1 and Vf1. So then measure the beta 1 angle. So then we draw beta 2 angle here and find out and mark the VR2 line. Then draw the alpha 2 angle, then draw V2, then Vf2 line. So now then finally measure the total length of delta Vu, that is Vu1 plus Vu2. So that from the graph you have to list out the values, that is the delta VU is equals to 128 meter per second. So from the molar chart, so because some pressure values are given here, so here for pressure 2.7 bar, so that is the dry saturated stream, that is X is taken as a dryness fraction is taken as X is equals to 1. The density is equals to, the density is calculated by using the value of 1 by specific volume. The V represents a specific volume here. So density value is 1.5 kg per meter cube. So now here the mass flow rate is equals to the rho into AF into VF. So here the M dot represents, that is a mass flow rate or steam flow rate through the turbine. So rho indicates density of the steam. So then AF is equals to area of flow, and VF is equals to velocity of flow. So now the velocity area of flow is equals to, the area can be calculated by using the formula pi into d of m into h. So here the diameter d, the mean diameter is here d. So h is equals to height of the blade. So then, so here the diameter is calculated by using this relations, so that is equals to 0.43 meter. So because here the mass flow rate is known, the density value is known, and velocity of the flow is known. In the area formula, the pi value is constant and h value is known. So for that reason, the diameter is only one unknown parameter here. By using that relations, we can find the value of diameter, that is 0.43 meter. So next, so what is the speed of the wheel? The speed of the wheel is given by n. The n is calculated by using the formula pi dn by 60. Correct, the pi dn by 60. See here the blade speed is known, and here the diameter value is known, and only one parameter, this n, is unknown. Then calculate the speed of the wheel. So that is equals to 1823 rpm. The second thing, you have to calculate the diagram efficiency, that is given by neta b. So diagram efficiency is calculated is like that. The energy input to the moving blade. So what is the energy input to the moving blade? So that is given by E. The E is calculated by using the equation, the V1 square by 2G plus VR2 square minus VR1 square by 2G. So because here the pressure drop or enthalpy drop occurs both in the moving blades as well as fixed blades. So for that reason, the energy transfer or energy input to the moving blades is given by V1 square by 2G plus VR2 square minus VR1 square by 2G. So now by using this relation, we can find the value of VR1 is equals to 53.32 meter per second, and total energy is equals to, so from the by substituting these values over here in a energy equation, we can find the energy input to the moving blade is equals to 6678.8 joules per kg. So what is the work done per kg of steam? So the work done per kg of the steam is calculated by using the relation, the W is equals to U into delta VU. The U is equals to blade velocity, and delta VU is equals to the change in tangential velocity. From the values obtained from the graph, it is substituted in the work done formula, and finally the work done is given by, it is calculated, that value is 5257.4 joules per kg. So now diagram efficiency is equals to, calculated the diagram efficiency neta B is equals to work done by energy input. The work done is equals to U into delta VU, and energy input is given by E, the W by the ratio of W by E. The value of W is equals to 5257.4, and energy input to the turbine is equals to 6678.8. that means the blade efficiency or diagram efficiency is equals to 78.7%. Then diagram power, that is P. The diagram power is calculated by, once again, the formula. The P is equals to M into W. So that is equals to 2.5 into the W is equals to 5257.4 by 1000. The answer is 13.14 kilowatt. The enthalpy drop of the steam, enthalpy drop of a steam in a stage, so that is the delta H is equals to the 5257.4 divided by 1000, that is a 5.26 kilojoules per kg. So this is the method of solving the numerical in reaction turbine. Now, second example or second numerical on reaction turbine. A 20 stage person turbine receives steam at 15 bar and 300 degrees centigrade, and steam leaves the turbine at 0.1 bar. The turbine has a stage efficiency of 80% and reheat factor is 1.06. The total power developed by the turbine is 10,658 kilowatt. Find the steam flow rate through the turbine, assuming all stage develop equal power. So that is the first part of the numerical. The second part of the numerical is steam pressure at certain stage of a turbine 1 bar is dry saturated. The blade exit angle is 25 degree and the speed ratio is 0.75. Find the mean diameter of this stage and also the rotor speed. Take the blade height as 1 by 12th of the mean diameter. The thickness of the blades may be neglected. So now list out the given data here. So here number of stages, the n is equals to 20 stage. There are the 20 stage persons turbine. The initial pressure of the steam is P1 is equals to 15 bar and its temperature is T1 is equals to 300 degree centigrade. And steam leaves the turbine or the condenser pressure is equals to 0.1 bar, that is a P2 is equals to 0.1 bar, and stage efficiency of the turbine is given, eta S is equals to 80%, that means 0.8. The reheat factor is, that is RF. RF value is 1.06 and total power developed by the turbine is 10,658 kilowatt. In second part of the numerical, the pressure, the steam pressure at certain stage is given, that is 1 bar, and dryness fraction is 1, that is a dry saturated steam. For that reason X value is equals to 1. The blade exit angle is 25 degree and speed ratios here, the beta 2 is equals to 25 degree, that is equals to alpha 1, because according to the 50% of the reaction turbine, because of the Parsons turbine. This is also called as what, the Parsons turbine. Then phi is equals to, the speed ratio is equals to U by V1 is equals to 0.75 and H value, the H value is equals to 1 by 12th of mean diameter, that is a dm, 1 by 12 into dm. And here the blade thickness is get neglected. Then find out the to find the mass flow rate here. The mass flow rate is calculated by using this method. The overall efficiency is equals to stage efficiency into reheat factor, that is equals to 0.8 into 1.06, that value is equals to 0.848. So according to the HS diagram, so here the initial pressure is a 15 bar and P2 pressure is a 0.1 bar and temperature value is given at inlet, that is initial temperature at 300 degree centigrade. So from this HS diagram, from the molar chart, so H1 is equals to the enthalpy at inlet is equals to 3035 kilojoules per kg, and H2 dash is equals to 2200 kilojoules per kg, and change in enthalpy, that is H1 minus H2 dash, is equals to 835 kilojoules per kg. Actual total enthalpy drop per kg of the steam is equals to total enthalpy change is equals to delta H1 into overall efficiency, so that is equals to 708.1 kilojoules per kg. The total power developed is equals to P of T is equals to mass flow rate into delta H T, that is the total enthalpy change. The total power now total power developed is equals to power developed total is equals to, that expression is equals to mass flow rate into total enthalpy change. So in this one, say power developed value is available in a numerical, the mass flow rate is unknown, and delta H, the total enthalpy change, is already be calculated, that is a 708.1 kilojoules per kg. By using that relations, we are getting the value of mass flow rate, so that is 15.05 kg per second. So this is the method of calculating the mass flow rate through the steam turbine. Now enthalpy drop per kg of steam per stage, that is a delta H, is given by total enthalpy change by number of stages. So how many stages are there here? So there are 20 stages turbine, so that is equals to 708.1 divided by 20 is equals to 35.4 kilojoules per kg. That means in a stage the 35.4 kilojoules per kg of enthalpy drop occurs. So coming to the second part of the numerical, so here mean diameter and rotor speed is calculated. So enthalpy drop per stage, so that is equals to also calculated by using the expression delta H is equals to W is equals to V1 square into 2 phi cos alpha 1 minus phi square by G. So here the total enthalpy drop already be calculated, that is a 35.4 into 10 to the power 3, that is equals to the V1 square into 2 into the phi value is given, that is a 0.75, and cos alpha 1 value also available, that is a 25 degree, the minus phi square, that is 0.75 whole square, and here G is taken as a 1 for steam turbines. So now with rest, then we are getting the value of V1 from this expression, that is V1 is equals to 210.8 meter per second. Now what about the U value? So here the speed ratio is equals to the ratio of blade velocity to absolute velocity of the fluid, that is U by V1. So now you know the value of V1, also know the value of speed ratio 5. So now easily we can find the value of U, so that is equals to 0.75 into V1, so that is equals to 158.1 meter per second. So from molar chart, for second case it is given the pressure is 1 bar and there is a dry steam. So with respect to that, the density value is equals to 1 by specific volume is equals to 0.59 kg per meter cube. So now VF1, the VF is equals to, we know the relation, the VF is equals to V1 sin alpha 1. So now we are getting the VF value as 89.09 meter per second. Then mass flow rate is equals to density into area of flow into velocity of flow. So here density is known, and area of the flow is calculated by using the expression the pi into mean diameter into h, height of the blade, and Vf represents flow velocity. See here, that is equals to rho into phi, that is a constant, then diameter. See, one more thing, the some relation is given for the h value. The h value is equals to the 1 by 12th times of the dm. So according to that, the rho, that expression becomes now rho into phi into dm, the mean diameter square, there is a Vf, the flow velocity, by 12. Then substituting these values in this expression, we are getting the diameter as 1.045 meter. And what about the wheel speed? Now wheel speed is calculated by using the tangential blade speed expression, that is u into 60 by pi into mean diameter. We know the value of u, we know the value of diameter, and finally getting the speed is equals to 2888 rpm. So this is method of solving the numericals in Parsons turbine or reaction turbines.